welcome to lesson 18 on the log normal distribution. If y is a normal random variable with mean mu and a positive standard deviation sigma, if x is equal to e to the y, then x has a log normal distribution, meaning that if we take log on both sides, we get that log of x has a normal distribution. Now we have some specific cases here. The graph of this of the density function of a log normal variable, and we see that it is not bell-shaped. It's not symmetric. Does not look like a normal curve. In this particular setup here, these graphs are skewed to the right, meaning we have larger frequencies values on the left and then the few outliers on the right. Now, we're going to be working with the normal distribution here, so recall the PDF of a normal random variable. And then this is the PDF of a log normal random variable. Notice instead of an x, they have a log x, they have an extra x in the denominator, and we'll briefly explain where that came from. So the cumulative distribution function when dealing with a continuous variable is the integral of the density. So if you take the derivative of the cumulative distribution function, you get back the density. So in the case of the normal, standard normal z, we have that the derivative of the CDF on the left is equal to the density on the right. Now we're making a change of variables here for z. Now again, instead of the traditional x minus mu over sigma, it's going to be log x minus mu over sigma because log x has a normal distribution. Derivative here is a chain rule. The derivative here of the outer function is just going to give us back the density of the inner. Derivative of the inside, derivative of log x is 1 over x. Everything else is a constant. Derivative of mu is 0, and then this sigma here in the denominator that's attached. That's an attached constant, so it stays attached. And so we get the density times 1 over sigma x by the chain rule for derivatives. And so that's why we have an extra x in the denominator here. The mean for the log normal is e to the mu plus sigma squared over 2. Variance is e to the sigma squared minus 1 times e to the 2 mu plus sigma squared. All right, an example. So a common example here where we may be able to use a log normal distribution. Income, usually a skewed distribution. Suppose income x in thousands is has a log normal distribution, mean 2, standard deviation 1. We're going to find the probability that x is greater than 20. We're going to find the expected value in the standard deviation. So we convert this over to normal by taking log. We know if x has a log normal distribution, then log x is normal. So we have this is equivalent to log x is greater than log 20. Since a log function is increasing, this inequality holds. So we use the z-score formula. Z is log x minus mu over sigma, so it's log of 20 minus 2 over 1. This comes out to about 1.00 rounded off, and then we use our z-score chart here to calculate this. Now, we wanted the greater than direction here, greater than. So we have to subtract here. It's going to be 1 minus the probability that z is less than 1. We looked that up on the table. Remember, in a continuous distribution, the probability of z being equal to any specific value is assigned as 0. So it doesn't matter if we have the less than or equal to or not here when we're dealing with a continuous situation. All right, so we look up 1.00, it's 0.8413 in that first column. In the 1.0 row, it's 0.8413. So the probability we want is the opposite side. Table always gives you the area to the left. We want the right. It's 1 minus the table value. 1 minus 0.8413, which is about 0.1587. Now, the next part was to find the expected value and the variance, standard deviation. So expected value of x is e to the mu plus sigma squared over 2. And mu was given as 2 and sigma as 1. So it's 2 plus 1 squared over 2. It's 2.5, 2 plus a half in the exponent. E to the 2.5 is about 12.18. Variance, e to the sigma squared minus 1 times e to the 2 mu plus sigma squared. So it's e to the 1 squared minus 1, and then e to the 2 times 2 plus 1 squared. So that's e to the first minus 1 times e to the fifth. Distribute that through, it's e to the 6 minus e to the fifth. And then the standard deviation, you take the root of that. The standard deviation is 15.96. All right, this concludes the section on the log normal distribution.